All right, guys. So, hope you're doing well. At this point, we've learned about the definition of a derivative with that limit of the f of x plus h minus f of x over h as h goes to 0. We've talked about the power rule, the product rule, the quotient rule, and the chain rule. A couple other rules about e to the x or a number to the x, like 2 to the x. How to take the derivatives of all of those. We've also talked about how to take the derivative of a natural log of a function, a natural log of x, or even a log base 3 of x. We've talked about all these things, put them into practice. I'm going to continue to review those before this first this first derivative test. And then we're going to have a second derivative test over trig derivatives and all that. But before we get into that, I want to talk about a couple of things today. The first one being differentiability of functions, which means certain functions you can't take a derivative. I mean, you can actually calculate the equation of the derivative, but there are certain places where a derivative can't be taken. We're going to talk about that today. We're also going to start talking about finding not just the slope of the lines that are tangent to the curves, but the equations of those lines that are tangent to the curves, which really shouldn't be a big deal because you already know how to find an equation of a line. But anyway, we're going to jump into that today, and hopefully it won't be a huge deal. Probably won't take as long. And to me, it's a little bit more simple, but just some basic applications, some basic definitions that I think you'll be able to hold on to. All right, without further ado, let's jump into differentiability of functions. Okay, so as you might have guessed so far, if I ever give you a function and say take a derivative of it, by the time we're finished with what we do in this course, you'll be able to take a derivative of a function. But remember that a derivative is this new function. It's basically a formula for calculating a derivative. Well, hypothetically, what would happen if the denominator that you got had an x in it? Well, if the denominator has an x in it, that increases the chance that when you plug something in for that x, that the function's undefined. Okay, well, if you think about it then it's possible to have a derivative function that has an x in the denominator in such a way that certain values, when you plug it in there, give you undefined values, which means the derivative wouldn't exist there. Well, when you're looking at a function, you should be able to tell if a derivative doesn't exist there as well, based on what we're going to talk about today. And the first thing we're going to look at is we're just going to think about the actual definition of a derivative, which remember is the slope of a line that's tangent to the curve. Now, the definition is more important than you might have thought. It's the slope, which means there can't be more than one slope. So when you look at a certain function, I'm looking at number 1, which resembles an absolute value graph, and we call a situation like an absolute value graph right where it changes direction a corner. But the big thing about a corner is it doesn't have to look like absolute value. It just has to basically have a slope coming in from one side that is different than the slope coming in from the other side. It could look like this. It could look like this. Right here, that's a corner right there. It could even be a really subtle change, but definitely a change. These places are all considered corners. Now, the rest of the graph's not a corner. The corner is just that spot right there, that particular location where the slope coming in from one side is different from the slope coming in from the other. Well, this is an example of a place where a function is not differentiable. So this particular absolute value function, it has a derivative in a lot of places. Like coming in here, the derivative at any spot here is a -1 because the slope's -1. The slope at any spot here is positive 1, right? But right there, the slope is undefined. You could try to draw a tangent line there, but think about it. I could draw all kinds of lines that are tangent or just touch that, and they have all kinds of different slopes. But this definition of a derivative is the slope of a line. So if there's more than one little tangent line than you could draw, that's an example of a situation where you would not be able to have a derivative right there. Okay? And by the way, you'll learn eventually how to take a derivative of an absolute value function, how to actually do that algebraically. And you'll see that it will have a place in the denominator right there. The derivative will have a denominator with an x in it, and if I were to plug that 0 into the denominator, the actual derivative would be undefined. But we'll get to that later. Okay, so the first place where a function can't be differentiable is if it has a situation like this, where it's a sudden change in direction at one location. That's an example of what we call a corner. Okay, and corners show up in stuff like absolute value functions, but more predominantly in piecewise functions where you have different pieces that are coming together. All right, now the second kind of a situation is similar to a corner, and this particular graph really looks a lot like a corner. You're like, wait a minute, it looks like the slope right there is about a -0.5. Slope right there is maybe like a +1 or +0.5, and they're different. But the difference here is what you don't see about this graph is if I were to like zoom in right here and then keep zooming in and getting closer and closer, what you end up seeing is this. This graph actually comes down, and for one split second, it really does stuff like that. It gets more and more steep until at some point, as you're zooming in over and over and over again, it's so steep right there. If you were to actually go and measure the derivative or the slope of the line right here, it's getting so steep. The slope from the left is approaching -infinity. It's so big, negative, and the slope coming in from the right is so big, but a +infinity. So not only are the slopes different from both sides, but they're undefined from both sides. So it doesn't look undefined in this picture, but if you were to actually graph that equation or something similar to it and zoom in more and more and more, you'll see that that bird graph gets more and more steep the more and more you zoom in on it. And it gets so steep, so it actually is going undefined there. So on a test, it's kind of hard to tell those, so I try to make them really obvious like this. But we call those locations cusps. And again, it only occurs right there at x = 0. This thing has a derivative everywhere else. But if you took the derivative of this, check it out. You know how to take a derivative of that. The derivative is 2/3 x subtract 1 -1/3. And how can you rewrite this? Well, you would leave the 2 on the top, right? You'd put the 3 on the bottom. And what's an x to the -1/3 mean? Well, that's an x to the 1/3 on the bottom, or a cube root of x on the bottom. Now, if this is the derivative, what's the derivative when x is 0? Well, sure enough, if you plug a 0 in there, you get 2/0, which is undefined, which means the slope is undefined at 0. So at a cusp, this is an example of where the slope is undefined. Okay? Now, a lot of times you won't know what the picture looks like, right? And you'll just have the function. Well, take the derivative and plug the number in. If you get an answer, great. If you get undefined, then there's something weird going on there. Maybe it's a cusp, maybe it's a corner, maybe it's something else. But if you're looking at the graph, hopefully you'll be able to look at sudden changes in direction like these three or corners, and then changes in direction, but it goes vertical. Like it actually goes, this slope becomes so steep right there, it borders on -infinity or +infinity. That's the difference between a cusp and a corner. Okay, now the third one is similar to a cusp in that it actually goes vertical. And if you look at this right here, you'd have to definitely zoom in, but if you zoomed in right here a lot closer, what you're going to see is this graph is doing more like this, right? So at that point, it almost looks like the tangent line is vertical, which means just below that point, like right here, it's huge, really big, like infinity. And just beyond it is also really big, like infinity. So this one doesn't actually change signs. It actually goes from positive, really big positive, to undefined to really big positive, unlike a cusp that actually has negative slopes changing to positive slopes. But other than that, they look very much the same. And if I were to take this and flip it over, you would almost look like a cusp, wouldn't it? If I were to flip this over to the other side. So the major difference between this is the graph, if you drew a tangent line right there, it definitely would be a vertical line. So it's undefined. Vertical slopes are undefined. And again, this is an example of the 1/3, x to the 1/3 graph. If you took a derivative of x to the 1/3, don't you get this? And if you simplified that, don't you get a 3 on the bottom with a 1 on the top? And this is a x to the 2/3 on the bottom, which is a cube root of x squared. And sure enough, what happens when you plug a 0 into this function? It's undefined, so the derivative is undefined, but only at x equals 0. Everywhere else, there are slopes, but not here. So those are the three places where a graph can actually have an x value there. It exists, but you still can't take a derivative. Corners, cusps, and places where the graph goes vertical. And by the way, a cusp and a corner is a good name. Going vertical is kind of a name that we've made up here at Homewood. Other people use it too. But you could also say that it has you could call this, instead of saying going vertical, you could say it has a vertical tangent line. Okay? Going vertical or vertical tangent line, those are the same thing, but there's no formal name like there is with corner and cusp. And then the last situation, to me, is kind of obvious. If the function is not defined there, like if you think about non-defined places on a function, vertical asymptotes, there's no graph there. Holes, there's no graph there. Jumps, even if there is a graph there, it's an endpoint, right? But all of these situations are places where the graph isn't continuous. So if it's not continuous, whether it's actually defined there or not defined at all, if there's no point, how can you take a derivative? Because the definition of a derivative is the slope of a line tangent to the curve at that point. So if there's not a point, then there's no derivative. So those are the four places where you are not allowed to take a derivative. And if you had an equation, you might not see it. A lot of people don't think about an equation. If somebody looks at this and they go, hey, is this a differentiable equation? It's very easy to say yes until you take the derivative and go, oh, wait, no, it's not differentiable, because there is a spot on there where this could be undefined, right? There is a place on this number 3 where it could be undefined. But a lot of times we'll have the picture, and if we have a picture and I say, hey, where's this function continuous? Well, I can take a slope, a derivative anywhere here. I can take a derivative anywhere here because at any one of these points, there is a tangent line that has a slope, but not at the vertical asymptote, not at the hole, and not at this jump, because these three places are not continuous. But everywhere else on this graph, assuming it keeps going, but also right here, what did I sneak in right there? This potentially could be a place where it goes vertical. See how it kind of goes like this and then goes straight up and down for one instant and then flattens out? So this is definitely defined. It's not non-continuous, but that would be another spot. Those four places, those four x values would be places where the derivative would not be able to be found. But these three x values, -5, 1, and 5, those would be where the graph is not continuous. Okay? So I'm going to walk through some examples of this, and then I probably won't talk a lot about it for the rest of the time we're doing derivatives, but make sure you review this for your test or keep this page handy since it's open notes. All right? At least in the year of coronavirus. All right, I'm going to flip the page and give you some examples. So here are just some random piecewise functions here, okay? So I'm going to just go through some different spots. So I'm asking you about -7 right here, but what if I asked you about like -9? Is this graph differentiable? Now, differentiable means that you're able to take a derivative. So if I asked you if it was differentiable at -9, you should say, well, of course I can, because there is a tangent line there, and there is a slope of a tangent line, so yeah. But what about -7? To me, that looks like either a corner or a cusp, because we really don't know what the function is that I've drawn here. It's just something weird. I would probably say cusp because it kind of looks like that cusp we had, but I would probably take on a test a corner or a cusp here, unless I really made it obvious and made it really steep, like maybe like this. Made it really steep on your test. Okay, so look for that. It'd be really obvious if I want it to be a cusp, but that was probably my intent on here, but I would have probably taken both. So is it differentiable at -7? No, it is not. Okay, now what about here at -2? Now at -2, the idea here was that this was going vertical, but I've had people over the years, this is hand drawn. I've had people say, Mr. Hurry, this is not vertical right there. It's got a little bit of a slant. And you know what, I kind of agree with you. If that's what you're thinking, if it was going vertical, I probably should have drawn it like that, where it really came up and really went vertical for a second. okay? But my intent was that it was going vertical, so my intent was for it to be no. But again, this is just kind of walking you through things. Now, what about any point in between here? Any point in between here, is it differentiable? Can you take a derivative there? Sure, because if I can draw a tangent line at any of these places, if I can, and there's just one slope to it, then I'm good. See right here, I can't draw just one tangent line. It's got all kinds of them. So cusp, no, it's going vertical. So I would say no, this is going vertical here. All right, and what about here at 3? Well, at 3, it looks to me like there's not even a point. So definitely no, I cannot take a derivative. Why? Because it's not continuous, right? If there's no point there, how can I take a derivative at that point? What about here at 6? At x equals 6, I got to say no again. Why? Because it's not continuous. You could say because there's a jump there, but the question said, say if it's not continuous, so I'm just going to say that. All right, coming down to the next graph, what about at -5? That's right here at the VA. Well, no, it's not continuous. Why? I mean, it's not differentiable. Why? Because it's not continuous. What about here at -1? I would say no. Why not? Because there's a sudden change in direction. The slope here, I don't know what it is. Maybe like rise 1 runs 4. Maybe it's a 1/4 coming here from the left. I'm making something up. And then right here, what's the slope look like? Maybe a rise 4 run 1. Maybe the slope here is a 4, but are they the same? No, there's a sharp sudden change. This is another example where it's not differentiable. Why? Because it changes direction. There's a corner. Now, if you're thinking cusp, even if it did go had a negative infinity slope here, it didn't have an undefined slope there. That's definitely a slope of like a 4th or a 3rd or 5th or something like that. Remember, to be a cusp, it would have to go undefined in both ways, or basically go vertical there and go vertical there. What about here at 2? No, why not? Why? Because it's not continuous. Okay? And finally, what about here at 5? Well, absolutely, it's differentiable. Why? Because there is a tangent line there, and a tangent line does have a slope unless it's vertical. So I would say, yes, it is continuous. I'm sorry, it is differentiable. All right? Jumping down here to number 9. We're just going to run through all these at -7. People go, oh, yeah, that's differentiable, right? No. Yes, there's a slope coming in from the right, but there's nothing there. It doesn't continue. It's not continuous. So no, not differentiable. Why? Because it doesn't continue past that. It's not continuous. What about here at 0? What about here at 0 right there? Well, yes, definitely differentiable. Look, there's a tangent line there. I don't know what the slope is. Maybe rise 1, run -1, so maybe a -1. So yes, it is definitely differentiable there. What about at 3? No, look, it's sudden change in direction. And if I had drawn it even better, it would have looked more like a cusp where it went vertical and then went vertical again. So I would probably lean towards a corner here just because this looks so flat. But definitely it is not differentiable, right? Not differentiable. And this particular thing, definitely, I would either say corner or cusp here. I would have given you credit for either one, but I would argue corner since the left side is not going vertical right there. And then finally at x equals 6, again, doesn't matter what's happening from the left and that there is a slope coming in from the left. Look, the right's going down forever, right? This is definitely not continuous. It doesn't connect. So no, why is it not differentiable? Because it is not continuous. And then the last 4, before we jump into the equations of lines tangent to the curve, at -6, clearest corner on the planet, so definitely no, not differentiable because there is a corner. And then at -2, no. Why? Because it's not continuous, right? There's a jump right there. Now, are these values in between here and here, or all those, or all those? Are all the stuff in between differentiable? Sure. There's derivatives there because there are tangent lines to the points there that have slopes. But not there, not there, not there. What about at x equals 2? Yeah, some people go, no, because the slope's 0. Guys, the slope is 0 is okay. It's the slope undefined that's not. So at x equals 2, is it differentiable? Yes. Slope equals 0, totally fine. And then finally, what about at 5? No. Why? Because there is a cusp there. At least it looks like a cusp to me. Okay? Hopefully that's helpful. Again, make sure you keep this handy and are able to answer those questions should they pop up on a test. But I probably will not review them anymore. I can tell you that a lot of times there's a great multiple choice test on the AP test that will say, list 4 places where a function is not differentiable. And you would just say, well, there's a corner, there's a cusp, there's a place where the graph goes vertical or where there's a vertical tangent line, or you could say that there are any other non-continuous location on the graph, whether that's a hole or a vertical asymptote or a jump or an endpoint. All right, so remember all those. Endpoints are non-continuous, jumps are not continuous, holes are not continuous, VAs are not continuous, lots of places where they're not continuous, and then also cusps, corners, and places where the graph goes vertical. All right? Okay, last thing, it's not going to take that long to explain it, but what we're going to be doing now, and this is a huge topic on the AP test, at least 5-6 points of the 42 points you need to pass will be something to the tune of find an equation of a line tangent to the curve, and they'll ask it a million different ways. So first thing I want to talk about is, does everybody know how to find an equation of a line? And hopefully you do, because finding an equation of a line involves you knowing what 2 things? A point and a slope, right? And if you know a point, you plug the x value there and there in the point slope form. And if you know a slope, you plug it there. Now, a slope can be found by doing what? Finding the derivative of the curve. Now, don't make the mistake of finding the derivative function and plugging that equation in there. We want to find the actual slope at this point. So we're going to use the point and the function to find that exact slope, and then we're going to plug the point and the exact slope in here. And that's it. That's the equation of a line tangent to the curve. So literally, that's all there is to it. Let's check out an example. So find an equation of a line tangent to the curve at the given x value. Now remember, notice that's different than me saying find the slope of the line tangent to the curve. The slope of the line tangent to the curve is just the derivative. The equation of the line tangent to the curve means I want the actual line. So what do I need first? I need a point. So if I gave you that question, did I give you a point or did I just give you the x value of that point? Exactly. I just gave you the x value. So what we want is the y value that goes with it. Well, that shouldn't be a big deal. If I've got an x, I just plug it in to actually find the y. So that's what I did here. I plugged the 3 in. I got 27 minus 3 times 9, which is another 27 minus 4. And I've got a y value of -4. And there is my point. Okay? So right there, if I wanted to, I could plug that into the, I could say y minus the -4, which is +4. Leave a space for the slope right there. And then I could say x minus 3. So I'm halfway there right now. Now the next thing I need to know is the slope. Now again, guys, the slope is the derivative. So the slope of this tangent line is the derivative. Well, let's take the derivative of it. So I go back up to my function, I take the derivative of it, and I get 3x squared minus 6x. Great. Do not plug this in for slope. This is the generic slope. I want the slope where? At that point. And since there's no place to plug y in there, I'm just going to use the x value and plug the 3 in there. So here I go, I plug the 3 in there, I get 27 minus 18 is 9. That's my slope. So all I got to do is take this slope, go back and plug it in there, and you can see that's all I did. I plugged x minus the 3, there's the y plus 4, there's the 9, and we are going to stop right there 99% of the time. And the only time I'm ever going to do anything more than that is if I just happen to have a multiple choice question and it's given in either one of these forms. And you remember that, that's point slope form, that's standard form. If the form looks different than that, then yeah, maybe distribute the 9 and put it in a form and see which one it matches. But please don't do extra stuff when you don't need to. Point slope form is by far the one that makes me and the AP calculus reader the happiest. Plus it cuts down on your options for making careless errors. Now, anybody got an idea what I do if the slope doesn't exist? Like what if the slope is undefined, but there's still a point there, like a place where there's a cusp maybe, or it goes vertical? Well, I've got to think through that. I can't write DNE in there. That doesn't make any sense. So we're going to have to think about that in a second. Or what happens if the slope is 0 there? Well, if that's the case, just plug a 0 in there and all of that goes away and I'm left with y plus 4 is 0 or y equals -4. But we'll talk about what to do on a DNE in a second. But we're just going to basically do a couple practice problems and then call it a day. All right? So here we go. I've given you 6 problems here. This is classwork. Your homework's very similar. But it says find an equation of a line, equation of the tangent line at a certain point. And I may have given you the x value like I did on 1, 2, and 3. I may give you the point like I did on 4, 5, 6, and 7. But if I give you the function, you need a point and a slope. So how do I find the point? Exactly. You plug the 3 in. And by the way, in case you're not used to function notation with just a y, you can say y of 3 just like an f of x. And that means, oh, you plug the 3 in for x, and this is going to be the y value that goes with that 3. So I'm going to plug a 3 in for x, and you can see that the y value that goes with 3 is 27 minus 6 plus 5. Well, 27 minus 6 is 21, plus 5 is 26. So my actual point is 3, 26. All right, so there's my point. Now what do I need? That's right, slope. So the derivative of y is what? 6x minus 2. But don't use that for your slope. I want the derivative of y where? At 3. So I can write that kind of like a function. The derivative of y when x is 3, plug that in and I get 18 minus 2 is 16. So now that I know my point and my slope, what do? Y minus 26 equals 16, x minus 3. And I am going to stop right there because that's the simplest, easiest way to write my equation of a line. All right, what about number 2? Okay, this time what did I give you? I'm telling you when x is -2, y is -3. Well, that's just the point. X is -2, y is -3. So I gave you a point. I think I said earlier I didn't give you a point here, but I actually did. All right, so now that I know the point, I can go straight to the derivative. So what's the derivative of y? 3x squared minus 2. But I need to know the derivative where? There. So at -2, I would plug a -2 in, square it, multiply by 3, and subtract the 2. So that gives me a 12 minus 2, which is 10. Now that I know the point and the slope, you should be home free. Y plus the 3, right there, equals 10 times x plus the 2. And there's your equation of a line. It's tangent to the curve. All right, now every now and then, you'll get a situation like number 3 where the derivative is a little bit more involved, and so is finding the point. Just be careful, okay? I've been every year cutting down and making my derivatives less and less nasty because there's really no point of it. But just take your time on this, show your work. So what do I need? A point, plug the 7 in. And again, guys, label what you're doing. Label what I'm doing each time. Don't say the derivative is that and then say the derivative is 16. Say the derivative is that and the derivative at 3 is 16. Here I'm saying y at 7, and I'm plugging the 7 in the top and getting 21 minus 2. And I'm plugging the 7 in the bottom and getting 28 plus 1. Okay, so that is my point. And notice how I'm showing my steps on everything. Now, how do I take the derivative of this? Ugh. All right, got to pull out a quotient rule. So the derivative would be low, d high is just a simple 3, minus high, d low is a simple 4, all over the low quantity squared. So if that's the derivative, what's the derivative at 7? So be careful. Just show enough that I can follow you. Plugging a 7 in, 28 plus 1 is 29 times the 3. Plug a 7 in there, 21 minus 2 is 19 times the 4. And then a 7 in there, 28 plus 1 is 29 squared. And at that point, you can pull out your calculator, clean it up. You'll have a calculator on this test. In real life, you probably wouldn't have had a calculator there, so you'd have to be extra careful. But in this one, I'm just going to take out my calculator, create a fraction, 29 times 3 minus 19 times 4, all of that over 29 squared. And it gives me that. Now, I probably want a fraction, at least to create the illusion that I've done the math, right? So I'm going to go right here. I'm going to go menu, number, approximate to a fraction, and it gives me 11 over 841. So 11 over 841 would be my slope. So therefore, take the point, take the slope, and here we go. Y minus 19 over 29 equals 11 over 841, parentheses, x minus 7. And as ugly as that looks, that's an equation of my line tangent to the curve. All right? Now, what do I have here on number 4? What did I give you? It looks to me like I gave you the derivative of y. That's dy dx. That's like y prime. So I'm giving you the derivative. And I already have the point. So I don't have to find the y value. So all I have to do is find the derivative at that point. Now, the way I write that with the dy dx is I don't use that fraction. I don't use parentheses. I do this. I write, okay, if that's the generic derivative or the derivative, then the derivative at, I draw this vertical line and I put the point right here, 3 comma negative 1. So the derivative at that point, you could also say x equal 3 because the 3 part's the only part that matters here. I can't plug a negative 1 in anywhere. So this is fine, or you could just say at x equal 3, right? You could put either one of those right there at the bottom of the line, and then you just plug the value in there. In this case, there are only x's in there, so I'm going to go, all right, 4 times, I'm plugging the 3 in, 4 times 3 squared, 4 times 9 is 36, minus 4 times 3 is 12, and on the bottom, 3 minus 1 is 2 squared is 4, so I end up getting 24 fourths or 6. Guys, that's my slope, okay? That's my point. So we're done. Y plus the 1 equals the slope, x minus the 3. And AP loves to give you situations like this where they don't even tell you the function. So the nice part is you don't have to find the derivative. They already gave it to you. All right? So again, there's my point. There's the slope. I calculated at 3, negative 1, or at x equal 3, and I plug it in. Okay, look at number 5. Number 5, I'm back to having the function again, but I do have the point, so I don't have to find the y value. I got to go straight to slope. So how do I find the derivative of this function? Well, looks like a product. Got to do a product rule. So first, d second. What's the derivative of that? Well, it's 2 blah to the 1 times 1. Remember, I take the derivative of the inside part, which is a 1, and then you decrease the 2 by 1, and that's a 1. So that's all that's left. So first, d second plus second, and then here comes the derivative of the first part. Well, the derivative of that, you got to start with 5. 5 blah 4 times the derivative of the inside part. All right, remember the chain rule? Now remember, again, technically I went 2 blah 1 times the derivative of the inside part, but I didn't need to write those two ones. So that's my derivative. Don't bother cleaning it up. Now I need the derivative at x equal 1. Technically it's at that point, but there's no place to plug a 4 in. There's no y value in this equation. So I want the derivative, which is the dy dx, at x equal 1. So let's plug a 1 in. Plug a 1 in there, and I get 3 minus 2 is 1. 1 to the 5th is 1. Plug a 1 in there, I get 1 plus 1 is 2. 2 to the first is 2. 2 times 2 is 4. 4 times 1 is 4. Then I'm going to go plus, plug a 1 in there, 1 plus 1 is 2. 2 squared is 4. Plug a 1 in there, 3 minus 2 is 1. 1 to the 4th is 1. 1 times 5 is 5. 5 times 3 is 15. And I end up getting 4 plus 60, or the derivative of 1 is 64. Okay, what have I got? A point, a slope, y minus the 4 equals 64, x minus 1, and you're finished. Okay, and then number 6, again, I'm going to zoom in. I can barely even see this on my screen. Okay, sorry. Number 6 right here. Okay, so I've got this function. I did give you the point, which was nice. So I've got the point. I don't have to find it, but I do have to find the slope. So what is the derivative of an exponential function? Well, the derivative of the e part is copy down the original problem. That takes care of the e. And then to take the derivative of that, which is the chain rule, you got to go to the inner function. You just take the derivative of that, which is a times 2. And if you put the 2 out in front, that's totally fine. That's how it'll probably look like eventually on a multiple choice test. All right, then if that's my generic derivative, I need the derivative where? At this point. And again, since there's only a place for x, I can say the derivative at 4. And I can go e to the what? 2 times 4 is 8. 8 minus 3 is 5 times 2. So my derivative is actually 2e to the 5th. So there's my point. There's my slope. Therefore, y minus e to the 5th equals 2e to the 5th x minus 4. And completely expect to see ugly stuff like that. All the time y minus the y equals the slope x minus the x. And this is very common to see ugly looking slope values, ugly looking y values or x values. Very common. You'll see pi's and e's and all kinds of stuff on the AP test. All right. And then lastly, we've got number 7. And if you're looking at number 7, again, they gave you the derivative and they gave you the point, right? This means when x is a -2, your y value is 5. Well, if I have the point and I have the formula for slope, how do I find the actual slope there? I take the derivative. I've already got the derivative, but I'm going to calculate the derivative at an x value of -2. So plug a -2 in here. 6 is still on the top. -6 minus 2 is -8. So I get a slope of -3/4. So y minus the y, slope, x minus the x. All right, so I hope that helps. Good luck on your work. I believe your homework is, you'll just have to check your assignment sheet, but I'm pretty sure it's the sheet that looks very similar to this one, but it says homework on it. There might be something else though, so make sure you check. All right, guys, good luck. And in fact, there very well may be something else. So definitely check what your assignment sheet says and good luck. Let me know if you have any issues. All right, see you, bud. See you guys.